Okay, right. We're on our kind of summary of this big section on waves now, and we're mostly talking about electromagnetic waves. So we're going to make sure that we've got our basic facts that we're happy with, so we can go off and have a go at some of these GCSE questions. Now I'll put this diagram on so you can see here all of the facts pretty much that you need to get in your head and remember. So we've got a measurement of wavelength. So we're remembering this spectrum in order, and it could be, and in this case the order is in decreasing wavelength. Okay, these numbers are getting smaller towards this end, and that is the same as in order of increasing frequency. The frequency numbers are getting bigger this way. Remember, a small wavelength means a large frequency. So we need to remember these in order. You've got a diagram here which is giving you a way of thinking about the size of these waves from kilometers long to hundreds of meters long for radio waves, all the way up to tiny numbers. Look, times 10 to the minus 12, times 10 to the minus 12, really tiny numbers. Okay, we're talking about wavelengths that are smaller than water molecules. And in this section here, we've got where do these things come from, or what are they used for, right? And all of this facts here, okay, we're going to try and hold in our head. So I'm going to come down to some key facts that we all need to remember. Okay, so when you're answering these GCSE questions in a minute, some of the questions are about remembering stuff. Right, so that's traditionally what we tend to, when we revise, we memorize, or we try to remember and commit to memory facts. Okay, so that's what I'm talking about here. Right, it's not everything about the questions, but it is important that we know these things. So the names of each part of the electromagnetic spectrum, and the easiest way to learn those is in order. So I've put a little mnemonic here, look, a little mnemonic to try and remember the names of these bits. If someone's got their mic on, maybe you want to turn it off, I think. Raging Martians invaded Venus using X-ray guns gives us our names of the bits. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Who's got their mic on? Can I mute them? Thank you, Henry. Okay, so if that helps you to remember the order, learn that. If you just think I can remember the order of the waves, make sure you've got them in order, and be aware that maybe we get asked for them the opposite way round. So they might be in a diagram starting with gamma rays, the smallest wavelengths, and going this way. Okay, and remember we said that the visible light is from red at this end, and that goes on the same side as the infrared and the radio waves, and all the R's are on the same side. Just like if we talked about the other end, the violet end of visible light are the shortest wavelengths we can see, and past violet is the ultraviolet that we can't see. Okay, so there's some tricks. Make sure we know that order. Okay, you've talked about uses of each one. Be a little bit careful here, okay? When we say, for example, microwaves, we can't write down a use of microwaves is microwaves, but we can say a use of microwaves is to cook food, okay? We can cook food with microwaves and with infrared, okay? Infrared, remember we did last lesson, is heat, okay? Whereas microwaves cook food by making the molecules get excited inside the food in your microwave oven and make them bounce about, which is what heat is. Okay, again, same thing. Don't say we use radio waves for radios. Say we use radio waves for carrying radio and TV signals, for communications. All right, so if an exam question is asking you about uses, you should have up your sleeve at least one use for each part of this electromagnetic spectrum. Okay? When we're talking about dangers, the thing that we mostly think about as a danger is ionization. That means changing the molecules in your DNA. And that can cause mutations, damage your cells, and increase the risk of developing cancer. When we talk about ionization, it's this end of the electromagnetic spectrum that we're talking about. Ultraviolet, X-rays, and gamma rays can cause ionization, damaging the DNA in your cells, causing them to mutate, and that's what cancer is. Okay, it doesn't mean that there aren't dangers down here. So very bright visible light can damage your eyes. Infrared is heat, so it might burn you. You wouldn't be able to fit in a microwave, but if you did, you would damage yourself. Okay, but the biggest dangers are this ionization caused by the higher energy waves at the end. Okay. Facts about the electromagnetic spectrum. All of the waves in the electromagnetic spectrum are transverse. Remember what that means from our last topic. It means the vibration that makes these waves is at right angles to the direction that the energy is traveling. The vibration, the oscillation, the disturbance is at right angles. They are transverse. All of the waves in the spectrum are transverse. I'm going to skip ahead to this one. All of the waves in the spectrum travel at the same speed, and light is part of that spectrum. So we know that they travel at the speed of light. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays all travel at the speed of light. Okay, and in our diagram we've seen the patterns of wavelength getting smaller towards gamma rays, frequency getting higher towards gamma rays, energy getting bigger towards gamma rays, and ionization being more at gamma ray end of the spectrum. Okay, so frequency, energy, and ionization, these three all get larger towards the gamma ray end of the spectrum. Okay, so as you go along the electromagnetic spectrum towards gamma rays, the frequency gets bigger, the amount of energy gets bigger, and the ionization potential gets bigger. Okay, the wavelengths is the odd one out, if you like, because remember, a big wavelength means a small frequency. So the biggest wavelengths are at the radio waves end, and the smallest wavelengths are at the gamma ray end. All right, okay, we're nearly there. Make sure you're happy with looking at very big or very small numbers. Maybe you're going to come across them in standard form or with units that aren't the standard unit. So if I said, you all know that if I said I've got 1 millimeter, that means 1,000th of a meter, or 0.001 meters. Okay, so you could have millimeters, kilometers, centimeters. Okay, and in the same way you can have some very small numbers like nanometers or micrometers, and these units are small. So if you need to look units up, do. A nanometer is a billionth, and a micrometer is a millionth. Okay, and we can have very large, we could write our millimeter like this, couldn't we? A millimeter is times 10 to the minus 3. Yeah, 1,000th, a millionth, a billionth, very small numbers. In the same that we can have very big numbers. So you're familiar with kilometers, kilometers. 1 kilometer is 1,000 meters. Yeah, but you might not know that you could have a megameter or a gigameter, and these correspond with these numbers here. So a mega is a million times, and a giga is a billion times. So 3 and a 6 and a 9, and a minus 3 and a minus 6 and a minus 9, those are our kind of units that help us to write very big or very small numbers without putting loads and loads of zeros or loads and loads of zeros after the decimal point in. Hopefully in maths you've done some work on writing big and small numbers like this. Remember, our units need to be meters for wavelength and hertz for frequency. Okay. In the last topic, we used the equation to link these things together, and we said that the velocity of a wave is equal to the frequency multiplied by the wavelength. And that's why the units are really important. We need our frequency to be in hertz and our wavelength to be in meters if we want our velocity to be in meters per second. Okay, and we put that equation into a triangle. Velocity is frequency times by wavelength, and we use that funny Greek letter lambda to represent the wavelength. Here's the wavelength, Greek letter lambda. This is how many meters long my wave is. This is how many times my wave oscillates per second, its hertz, and this would be its speed in meters per second. In the electromagnetic spectrum, the velocity is constant at the speed of light, 300 million meters per second. Okay, and that explains why a bigger wavelength has to be a smaller frequency, because the velocity is constant all the time. And then last lesson you looked at infrared, and you should have concluded from your work that if something is hot and it's painted black, it gives out infrared better. Black surfaces are the best emitters of infrared radiation. If something is hot and black, it emits infrared better than something that's hot and white or hot and shiny. Okay, if something is cold and you paint it black, it will be the best at absorbing heat from the surroundings. If something is cold and it's black, it will warm up faster than something that is cold and white. And we talked about the fact that sometimes you want things to stay cold and other times you want them to warm up. So fridges tend to be white because you don't want them to absorb heat. So white fridges are white because it is the worst absorber of heat, and so it stays cold easier. If you've got a black fridge, it might fit in with your kitchen, but it's probably slightly more expensive to keep going because black surfaces will absorb heat from the surroundings faster than white ones. Okay, let's have a little look at a question and then you can have a go at some. Okay, so think what we've just been talking about, our facts. You're going to have a go at this question in a minute. The diagram below shows the position of 3 types of wave in the electromagnetic spectrum. Okay, so we're thinking, I know the order of this. It started with radio waves, so I could fill these in. I'd be thinking to myself, right, radio waves, what comes next? Microwaves is A, and then infrared, then visible light, ultraviolet X-rays, and D would be gamma rays. So I could name all of those parts, and that means I can choose which of the boxes is right for visible light. Or I might think, well, there's ultraviolet, one back from ultraviolet, that will be the visible light there. Which one of the statements about electromagnetic waves is correct? Okay. All of the statements are about wavelength and frequency. Let's go back to our spectrum here. We know that the radio waves have the biggest wavelength and the smallest frequency. So let's have a look here. Which ones can we discard? Radio waves have a higher frequency than X-rays. Well, that can't be right. Radio waves have a longer wavelength than ultraviolet. Well, that is true. Okay. So I'd be going for this one. I'm going to check these two. X-rays have a longer wavelength than radio waves. Well, we know that's not true because these are the shortest wavelengths at this end. X-rays travel faster. Well, I've discounted that because I've remembered that all of these waves travel at the same speed. So I'm going to be able to choose the correct box here by remembering my patterns about frequency and wavelength and the fact that all of these travel at the same speed. A danger of exposing your skin to ultraviolet. So here I'm remembering my fact that ultraviolet does that thing. It is ionizing. What is the danger? It might ionize my DNA, change the DNA in my cells, cause my cells to be damaged and mutate. A danger of exposing your skin to ultraviolet radiation is that you increase your risk of developing skin cancer. Okay, now the next part of the question might not require you to recall facts, but now the skill here is to look at the data and see what it means. Let's understand what it means. Having an X-ray taken exposes a person to ionizing radiation. That's bad. The table below gives the average radiation dose, that means how much you get, for an X-ray of the chest and an X-ray of the upper digestive system. Here we go. We've got some facts. The risk of an X-ray causing cancer is about 1 in 20,000 for each millisievert of radiation received. Compare the risk of developing cancer from having an X-ray of the upper digestive system compared to having an X-ray of the chest. So we must use these numbers. When it says this in an exam question, use the data, I must be doing something with these numbers. Think what your maths teacher might say. Your maths teacher might say, how many times bigger is the radiation dose for the X-ray to your digestive system compared to the radiation dose for your chest. How many times bigger is 5 than 0.1? Okay, how would you work that out? What would your maths teacher say? Your maths teacher would say, how many times does 0.1 go into 5? Okay, so we could do something with those numbers and get a value, a number, which gives us an idea about how many times bigger is the risk. Okay, so see what you can do with these questions. Right, if we go and look, we're not going to go through all of them because you're going to have a go, but the questions are all very similar and you're going to be remembering the facts we've been talking about from the start. Okay, so